gravimetric analysis. It's the analytical technique based on the measurement of mass. You typically use it for formation, isolation, and mass determination of a precipitate, which is something that you've done several times already this year. It is a highly accurate technique because the mass can be measured accurately. It's only good for reactants that go to completion. In other words, it's not good for reactants that are reversible or that you have, for some reason, your reactants not completely reacting. Alright, so if we look at this example, a sample of 0.3220 grams of an ionic compound containing the bromide ion is dissolved in water and treated with excess silver nitrate. If the mass of a silver bromide precipitant that forms is 0.6964 grams, what is the percent by mass of bromine in the original container or compound? So we have this precipitant of silver bromide. All of my bromide ion that was in the original ionic compound is going to go into the silver bromide. So I can set up some stoichiometry. So we have grams of silver bromide. We're going to convert it to moles of silver bromide. So the molar mass is 187.8 grams. That is 1 mole. For every 1 silver bromide, we have 1 bromine. And for every 1 bromine, I guess you could call that an ion. Oops. You have a molar mass of 79.9 grams. So that gives us a mass of 0.2963 grams of our bromine ion that was in the precipitant. So we're going to take our mass found in the precipitant, divide it by the mass of the total compound, times it by 100. And we have that it's 92% bromide. Now this doesn't tell us what the actual ionic compound is. So one thing that we could do to figure out the original ionic compound is have a list of bromine compounds available, and then we can use the mass percent of the bromine compounds and match up which one has a 92% bromine mass. An acid-base titration, you could also have a redox titration. So titrations are when you take a solution of known concentration, or the standard solution, and it's added to another solution of unknown concentration until the chemical reaction between the two solutions is complete. It's complete when you reach the equivalence point, and that's the point at which the acid has completely reacted with or been neutralized by the base. How do we know that we've reached the equivalence point? There's typically a color change by the indicator, and an indicator is a substance that has distinctly different colors in acid or basic solutions or media. So you're adding this indicator to the solution being titrated. It doesn't have anything to do with the reaction itself, though, except that it changes colors if it's in the presence of an acid or a base. Phenolphthalein is the indicator that we use in Chem 1, so it's clear when it's in an acid and it turns pink when it's in a base, but there's a lot of other different types of indicators as well. So how many grams of KHP are needed to neutralize 18.64 milliliters of a 0.1004 molar NaOH solution? KHP is a compound, that's the abbreviation for the compound, and the name of the compound is not coming to me right now. But we will run into KHP later on in the course. So how many grams? If you notice, there's 1 hydrogen and then 1 hydroxide, so it's a 1-to-1 ratio within the reaction. So I can figure out the moles of my NaOH by multiplying, because we know molarity is moles per liter, and then because we know it's a 1-to-1 ratio, I know that I have the same number of moles of KHP. And then all I need to do is convert it to grams. Alright, so KHP is potassium hydrogen thiolate. You would have to be told the molar mass because I'm not expecting you to know the chemical formula for that, and that's missing from this problem. So 1 mole of KHP has a molar mass of 0.2 grams of KHP. So that's the molar mass of KHP. And I've never seen an AP question that didn't give you that molar mass. So we have a mass of 0.382 grams of KHP. How many milliliters of a 1.28 molar sulfuric acid solution are needed to neutralize 60.2 milliliters of a 0.427 molar KOH solution? So here we're looking for milliliters instead of grams. So this is like a dilution problem, M1V1 equals M2V2. However, it's an acid-base problem, so we have to take into account that we have 2 hydrogens here and 1 set of hydroxide. So we typically say NaMaVa equals NbMbVb. N is the number of moles, and because this is an acid-base reaction, it's the number of moles of hydrogens for our acid and the number of hydroxides for our base. So then we can just plug in our numbers. We have 2 hydrogens for our acid solution, so we would say 2 times. The molarity of our acid is 1.28 molar, and we're trying to find the volume. The number of hydroxides in our base is 1. The molarity is 0.427. And our volume is 60.2 milliliters. Again, when you have your dilution reaction, you don't need to convert to liters. And if you solve for the volume, you would have 10 milliliters. A redox titration is very similar. You have, except the redox titration involves the transfer of electrons, where the acid base involves the transfer of protons, or the H+. So we can titrate an oxidizing agent against a reducing agent, just like we can titrate an acid against a base. The equivalence point is reached when the reducing agent is completely oxidized by the oxidizing agent. Now, 2 common oxidizing agents that can be used because they could be treated as an indicator, they change colors when they're reduced, is permanganate, and then it turns into the manganate ion. So that's the one that we saw in the lab for this unit. It goes from a purple to a light pink. The dichromate ion can also be used because it goes from being a yellow-orange to being green. You treat the problem the exact same way that you would do an acid-base titration. So how many milliliters of 0.206 molar HI solution are needed to reduce 22.5 milliliters of a 0.374 molar potassium permanganate solution? The one thing you have to be careful about is the mole ratio. So I don't always like to do these as M1V1 equals M2V2. So the first thing I'm going to do is figure out the number of moles of my potassium permanganate. So I'll take my molarity and I'll multiply it by my liters. Oops. That's 0.0225. That tells me I have 0.00842 moles of KMnO4. And then it turns into stoichiometry. There are 2 moles of KMnO4 to every 10 moles of HI. So that gives me 0.0421 moles of HI. And I'm looking for the milliliters, so I know that moles divided by my molarity, which is moles per liter, so the moles will cancel, leaving me with liters. That gives me 0.204 liters. The question though asked me for milliliters, so I'm just going to convert that. So 204 milliliters.